Welcome to Spaceverse, your portal to cosmic adventures. At this point in time, not even a Nobel winner in physics will support our current understanding of the universe, and everyone knows it since it has happened in the sky. Adam Rees, on the other hand, is the most perplexed of all participants. The James Webb Telescope is discovering more and more space formations that are found to be in opposition to the conventional theory of cosmology. On the other hand, how is it that hypotheses that have been repressed for a long time regarding designs for the universe that were previously unfathomable are now being shown to be correct? In light of these puzzling findings, what does the future hold, and have our previous hypotheses ultimately been proven not to be correct? Answering even the most basic questions can be somewhat challenging. In spite of the fact that the topic appears to be straightforward, the rate at which the cosmos is expanding is a fundamental research mystery that has fascinated scientists for decades. The expansion of the universe has been demonstrated beyond a shadow of a doubt by contemporary scientific research. This expansion has been going on for approximately 13.8 billion years, when the universe was first created. The galaxies are likewise moving away from one another at a rate that is proportional to the distance that separates them from one another. Since Galaxy A is located 2 times further away from Earth than Galaxy B, it follows that its distance from us is also increasing at a pace that is twice as fast as that of Galaxy B. The American astronomer Edwin Hubble was one of the first people to recognize the connection between these two phenomena. To calculate the rate at which 2 galaxies are moving apart, one must first establish the distance that separates them, and then someone must be aware of a constant that can be multiplied by this distance. The so-called Hubble Constant is significant in this particular setting because of its relevance. In addition, this is the time at when things start to get obscure. The exact magnitude of this constant has been a source of debate for a very long time, even among qualified experts. You should keep in mind that the readings that came before were completely contradictory to one another. To put it another way, the outcomes that we come up with are contingent on the technique. One of these methods is based on the cosmic microwave background radiation as its principal component. This piece of evidence, which is believed to be conclusive proof in favor of that theory, is known as an essentially isotropic residue from the time of the Big Bang. By plugging in the current rate of cosmic expansion, we arrive with a value that is around 67 kilometers per second per megaparsec. 1 megaparsec is equivalent to 3.26 million light-years. 1 light-year is approximately 9.46 trillion kilometers, and 1 light-year is approximately 9.46 trillion kilometers. The expansion rate, on the other hand, suddenly becomes 73 kilometers per second per megaparsec if we measure distances in space using so-called Cepheids, which are stars that undergo completely periodic fluctuations in their brightness. Therefore, it would appear that the universe is expanding at a faster rate in close proximity to Earth, up to a distance of around 3 billion light-years, than it is expanding overall, which is obviously not the case. As of yet, no one has been able to provide an explanation for this unexpected departure, which is referred to as the Hubble tension. This mismatch between the various figures has been seen. This is what the James Webb Telescope has the potential to reveal about the universe. At first, it was believed that the mystery surrounding the expansion rate was the consequence of a measurement error made by the Hubble Space Telescope. However, now some specialists believe that this is not the case. Adam Rees had various goals, one of which was to investigate the likelihood of an error making its way into the data sets collected by the Hubble Space Telescope. Additionally, 2 other researchers were awarded the Nobel Prize in Physics in 2011, and one of them was a physicist from Johns Hopkins University in Baltimore. There is evidence that the expansion of space-time is accelerating, and scientists have discovered this proof. Rees and his colleagues utilized the James Webb Telescope in order to discover the factors that led to the enlargement of the Hubble Space Telescope, and to identify any measurement errors that may have been made by Hubble. On the other hand, how exactly does one go about determining the rate of expansion of the universe? In this instance, we make use of the so-called cosmic distance ladder. Due to the fact that each step of this ladder builds on the one that came before it, there is a consistently present possibility of making a measurement error. It is only up to a certain point that the Cepheids that have been specified can be trusted. This occurs as a result of the fact that accurate measurements of distance become more difficult to achieve as the distance rises. The light that emanates from the Cepheids becomes more diluted and less apparent as one moves further away from them in comparison to the light that originates from other stars. The good news is that Webb is 100 times more effective than its predecessor in the scientific community, Hubble. It makes it possible for scientists to investigate the most intractable mysteries of the universe with greater depth and precision than they were able to do in the past. According to the findings of the current study, which were published in the Astrophysical Journal Letters, the picture that was provided was somewhat disheartening. The James Webb Space Telescope, JWST, did not find any errors in its measurements, and it now encompasses the whole region that Hubble had previously found. An answer that is both succinct and significant is provided by Adam Rees for the continued strain that Hubble has been experiencing. It is possible that our grasp of the universe is limited. In addition to this, we need to solve the problem of how to connect the Big Bang to the current day and determine whether or not there is something that we have overlooked in our earlier research. It is no longer possible for us to have faith in Einstein's theory of gravity as a result of this answer. It is only natural that there are other scholars who are concentrating on the mysterious Hubble tension in addition to those who are linked with Adam Rees. After academics from Bonn and St. Andrews attempted to solve this mystery, a new possibility has surfaced as a result of their efforts. Our blue home planet would be located in a bubble-shaped region of space where there is a scarcity of substance, according to a more accurate description. The gravitational forces that emanate from the matter cause the galaxies that are contained within the cosmic bubble to be drawn towards the edge. This results in a higher density of matter in that particular region. Consequently, they are likewise moving away from our neighborhood at a rate that is significantly faster than what was anticipated. Despite the fact that this makes perfect logic, it also brings up new problems regarding how to proceed with the research. This is because the model that is currently being used does not take into account underdensities or bubbles of this kind. From a practical standpoint, they should not exist at all. There should be a uniform distribution of matter throughout space, rather than the opposite. Albert Einstein's theory of gravity forms the fundamental basis of the Standard Model, but it's also conceivable that the actual behavior of gravitational forces differs from what Einstein anticipated. Researchers look to a revised theory of gravity put out by Israeli physicist Mordechai Milgram in the 80s as a result. Even if it correctly predicts the existence of the associated bubbles, the so-called modified Newtonian dynamics has not yet acquired more than outsider status. All the debates regarding Hubble tension would likewise end if gravity truly does act in accordance with Milgram's theories. Actually, there would be just one constant for the expansion of the cosmos in this setting. The observed disparities would be caused by inconsistencies in the distribution of matter. How widely this new technique is validated and embraced will be revealed in the future. However, delving into the cosmic past also reveals the immense amount of unanswered questions that lie ahead. 14.32 The Universe Breakers. Even the most seasoned astronomers might be taken aback by a single number at times. In particular, the galaxy JWST 14-0 has a record's redshift of 14.32, which indicates, without more information, that this cluster of stars was already there 290 million years after the Big Bang. Simultaneously, there are several important concerns regarding the first known galaxy. How on earth could something so huge and brilliant have been there all that time? From where did the essential substance originate? The structure, which was found by the near-infrared camera NIRCam on the Hubble Space Telescope, most likely gained its current size after a period of 100 million years. When everything is taken into consideration, the galactic newborn is in direct opposition to almost every potential theoretical model and computational simulation of the early cosmos. The universe is actually one of the most enjoyable places to spend time with. Even the 6 galaxies that the James Webb Telescope had previously added to the star maps in the beginning of 2023 were far larger than they should have been. Despite the fact that the cosmos was only 500 to 700 million years old when these formations were constructed, they were very similar to our Milky Way. The galaxy JWST 14-0, on the other hand, has earned the nickname Universe Breakers among astronomers due to the fact that it defies all logic and reason in conventional cosmology regarding its existence. It came as a surprise to the researchers that they did not discover any unexpected infant galaxies, rather they discovered amazing objects that contained a star mass of approximately 10 billion solar masses. In the event that one of them weighs more than 100 billion solar masses, it is not impossible. In light of the fact that the presence of even a single one of these galaxies would push the limits of our understanding of cosmology, the question of how this was ever even imaginable needs to be answered at this point. An early cosmos with a matter density that was up to 5 times higher than what is indicated by current theories is the only possible environment in which the structures could have been discovered. On the other hand, it's possible that the galaxies expanded in some way that we haven't even discovered yet. The wider significance of modern studies on the Big Bang theory and galaxy formation. To what extent do studies on the Big Bang theory and the history of the early cosmos impact our broader understanding of the universe? Are we required to start anew in our quest to comprehend the formation and evolution of galaxies? As we delve into this complex topic, we need to examine the implications of recent discoveries and their influence on our current models. The ancient telescopes and ongoing mysteries. Historically, telescopes have played a crucial role in our understanding of the universe. Ancient telescopes, though rudimentary by today's standards, laid the groundwork for modern astronomy and cosmology. They allowed early astronomers to observe celestial phenomena and record data that would eventually lead to groundbreaking theories about the cosmos. In the present era, however, we face an array of ongoing mysteries concerning the universe's evolution. Recent advancements in technology, particularly with telescopes like the James Webb Space Telescope, have provided new insights into the early universe. Yet, these discoveries also reveal gaps in our current understanding, particularly regarding the formation of galaxies and their dark matter halos. The evolution of galaxies, from halos to stars. Our current models of galaxy formation start with the concept of dark matter halos. According to these models, dark matter began to clump together shortly after the Big Bang within the first few 100 million years. These halos, formed by the gravitational attraction of dark matter, served as the initial scaffolding for the universe's structure. Normal matter, primarily hydrogen and helium, was subsequently drawn into these dark matter halos due to their gravitational pull. As the gas accumulated, it eventually cooled and collapsed to form the first galaxies and stars. This process, however, was far from instantaneous. It took several 100 million years for the first galaxies to form, and even longer for these early structures to evolve into the large and complex galaxies we see today. Recent discoveries and theoretical challenges. Recent observations, particularly those made by the James Webb Space Telescope, have uncovered galaxies that appear to have formed much earlier than previously thought possible. These findings challenge existing theories and suggest that our understanding of the early universe may need substantial revisions. The discovery of such massive galaxies in the early universe implies that the process of galaxy formation may have occurred more rapidly than our models suggest. If galaxies existed at such an early stage, it would require a significantly larger number of dark matter halos in the early universe than our earlier models predicted. This discrepancy indicates that our current understanding of dark matter and its role in galaxy formation might be incomplete. Reevaluating the Big Bang theory and galaxy formation. Given these new observations, we must consider whether our models of the Big Bang theory and galaxy formation need to be reevaluated. Are the current theories inadequate, or do we need to adjust our understanding of dark matter and its influence on galaxy formation? The challenge lies in reconciling these new discoveries with existing theories or developing new models that better fit the observed data. One possible direction is to explore alternative models of dark matter or modifications to our understanding of how dark matter halos form and evolve. Additionally, we may need to refine our theories about how normal matter interacts with these halos to form galaxies. This process could involve integrating new observational data with theoretical models to create a more accurate picture of the universe's early evolution. In spite of this, there are certain experts who find it difficult to completely argue against the long-standing scientific consensus. Julian Munoz, a former student at the University of Texas in Austin, is a member of this organization. Perhaps we ought to exercise caution in the manner in which we interpret the data that Webb has provided to us. His line of thinking is founded on the following. If the early universe actually included 10 times more dark matter structures than was previously believed, then the number of galaxies that are visible in the Webb photographs would also be 10 times higher. On the other hand, if this were not the case, then it would likewise be the case with regard to the Hubble data. Through the utilization of a wide range of brightness levels, Munoz and his colleagues were able to accurately count the quantity of galaxies that were spotted by Hubble. The researchers' next step was to incorporate additional dark matter halos into their model of the early cosmos by adding more of them. Could it be the problem? On account of the halos that were necessary to correlate with the data collected by Webb, the data that Hubble had gathered was rendered unusable. However, which telescope offered the highest level of dependability? Webb is undeniably more powerful than its predecessor, but it didn't start providing scientific data until 2022. The Hubble telescope, in contrast, has been peering into the vastness of space for nearly 35 years. Munoz claims that at this stage, quantity is more important than quality, and the data from Hubble appears to be even more trustworthy right now. Because of this, we should stop trying to change the universe's history and start seeking for other, less drastic solutions to the mystery of the early galaxies. Remember that our knowledge of the cosmos is limited and evolving as we try to make sense of these enigmatic phenomena. Although the findings of the James Webb Telescope are questioning our long-held beliefs, they are also revealing previously unknown information. This is the very heart of scientific advancement, the necessity to tweak or even rethink our models. Our understanding of the universe is expanding with each fresh observation. A heartfelt thank you for being here with us today as we come to the end of our journey at Spaceverse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.